Nice. I can do a little intro for you.
Sure.
So yeah, we're happy to have Nikita with us today. So he recently finished his PhD at EPFL in the computer vision lab at Pascal Foy. He's also had a bunch of industry experience, Samsung, NVIDIA, Apple. Did I miss one?
Amazon.
Amazon. So a lot of experience. So also maybe an opportunity to chat with him after if you want to know what it's like to work at those companies. So he's going to be talking to us about several topics on computer vision and also a bit about his own research as well too. So I'll hand it over to Nikita.
Thank you very much for the introduction. Can you just check that? So you can see me, right, on Zoom?
Yeah, I see.
Can you hear me? Hopefully, yes. Guys on Zoom, can you just, I don't know, text something on Slack? Oh, sorry, on Zoom? Just
Yeah, we can hear you.
Yeah, I think someone told some. Yeah, okay. Yes, I think introduction in terms of who am I was rather comprehensive. Today, I would like to give you a presentation about general topic of computer vision. I try to gather some topics which are, I hope would be of interest of yours. Yeah, here I put just some of them: diffusion, perception, and safety. As far as understood in these lectures before, you didn't really have diffusion, at least what that was Peter told me. So I really wanted to kind of start with this, and then I really would like to give you a short introduction into topics I was working on throughout my PhD and my experience in companies. So yeah, the outline is going to be 4 big parts. First, I would like to talk about diffusion models, as I mentioned. We will have a short notebook for you to try it out, just to see and, I don't know, play it yourself. And then I want to just show you a couple of things about visual perception and current problems we have. In particular, one important problem of generalization, let's say. The third part is going to be about generalization. What is this? What are the current approaches? And we also will try one of them. And as the last part, I want to talk about uncertainty estimation, which is the topic of my PhD. I just want to give you a very high level understanding of what is this, why it's important, and what can we do with it. So at first, general terms. In general, when people talk about computer vision, we talk about convolutions. It's kind of the general and probably the most basic thing we use in computer vision domain. Probably, I guess, all of you know what is this. Can you raise your hands? Okay. So yeah, on a high level, what is this? We represent our data or images as tensors, and we convolve them with some other tensors with the learnable weights in order to produce more high-level representations of our data. If we would take a closer look, you can see how it works like this. We just basically align them together, sum them up, and generate a value which we kind of use further in our network as activations. And why we do this, the general kind of goal of this kind of activations learning, let's say, is learning some meaningful filters, right? As you can see here, those are learned filters, as far as I remember, from some model trained on ImageNet. You can try to give them some interpretation. It's up to you. But the point I wanted to make here is that we really want to learn the model that would map our images into something meaningful for our particular task, let it be a classification task or some other problems like depth estimation or etc. But in general, as I said, people start computer vision, let's say, presentations talking about these basic things. But then when I was putting those slides together, I thought that it could be a bit more, it could be a bit boring, let's say, because as I assumed, you know all this, what is activation functions, what are convolutions, how we use them together, etc., etc. So instead of giving very long and I suppose boring introduction, I thought that we can just jump right into this. And so we'll start with the diffusion models right away. First question, raise your hands who know what is diffusion models? Not everyone who heard about diffusion models. Yeah, not everyone. Who doesn't know what is diffusion model? Okay, that would be interesting. Then I will try to explain it from more practical perspective, like you will try it out yourself. Okay, maybe the last question, who thinks that you know how it works? None of you, okay, which is probably good. Let's start with the general kind of definition of the problem we're trying to solve. We can assume that we have some kind of data. As an example, maybe visual example is we have a bunch of images we collected from, I don't know, from real world. And we have some data distribution over this data, right? For example, you can tell that the image of random noise is less probable to find on internet than an image of a cat. So from this motivation, you can see that some images are more likely than other images. Here's more on top. There's a more like simpler example of such a distribution. Let's say when we have some scalar value, I don't know, temperature value throughout the month of February, let's say, and we want to generate a plausible temperatures, I don't know, in the same month of February. The goal, the objective of our task is to learn how to generate such inputs. In an example with images, we want to be able to generate plausible images of cats or whatever, something you actually do whenever you use ChatGPT and ask it to generate you an image. Yeah, I have some problems with clicking. Okay, the general kind of idea of all of those, not only diffusion models, but the generative modeling, generative AI, which you probably heard, the term you heard a lot throughout these 2 years, I guess, is to start with some noise and learn how to map it to something plausible. For example, map your noise into the distribution of real world images. Here on the left, you can see that's a representation of a noise, and on the right, the blue one is pretty much distribution of images, for example. I guess, I hope at least that you heard this term called GANs. Raise your hand who heard it. Okay. I think if we would consider GANs nowadays, it would be a bit on an outdated approach, I would say. So before diffusion, it was very popular to use it to generate, for example, images. The idea, we are not going to dive into details about the approach itself. The idea was on a high level that we want to start with some random noise and just pass it through the network and get a plausible image. So basically in one shot, just one inference of the model. And this approach was not, it was okay, was working to some extent. But at the same time, when we kind of reached the era of diffusion, we observed that we can do better. The major problem of GANs, at least nowadays, we kind of explain it like this. It's training instability. It was harder to train GANs compared to modern diffusion models. And therefore, GANs is an approach. It's kind of, as I already said it, it's kind of outdated idea. So let's switch to diffusion model. The idea, as I said, compared to GANs, instead of trying to generate something like generating an image, instead of generating it in one shot, like with just one forward pass of the model, we try to break it down to simpler steps. And we pretty much generate an image like in T steps. We make N or T inferences in order to generate the final prediction, final generated image. You probably, if you heard about diffusion, I guess you saw those plots when we have very noisy something, and throughout the steps we gradually generate something more clear and clean. As you can see here, we have T steps. We start with okay, let's start with the definitions. We have two processes, forward process and backward process. When you, for example, generate an image using ChatGPT, you actually do the backward one. So you start with noise and it gradually generates you an image. The kind of inverse process called forward process, when you start with a plausible image and you turn it into complete mass, complete random noise. But yeah, general idea is that we try to map this noise we have on the right, which is in general something like Gaussian noise, something very simple. We try to map it to something more plausible as images of a cat. It's actually a representation of what I showed you just a couple of slides before. So why it's better, just to emphasize it, we try to break it down to many steps instead of just trying to solve the task right away, like in one forward pass. We try to make it simpler, break it down to simpler steps. So if we are not really familiar with diffusion models in general in the audience, I guess you don't really have to understand this formula here. There's a text which I put here just to explain what's happening. The idea is that when you go from the step, I don't know, step 1 to step 2 or step t-1 to step t, what you basically have is that you add the Gaussian noise to your image, and that's pretty much the whole slide. So we just claim that the distribution of the image on the step t is generated from the previous step with adding some Gaussian noise with some variance and some mean value, basically. So when we work with diffusion, as I mentioned, we have these two steps, forward process and backward process. We will get to backward process in a second, but when we talk about forward process, there's like 4 steps we use to run it. The first step is just you have some training data set which contains, I don't know, millions of images of random images from internet, let's say. You just sample one of those at each step of each training step, and you add noise to it, right? As you can see, there's like 2 images on top and below it. You start with some clean image and you add some noise to it. You can see this noisy, I don't know, elements of it. That's pretty much the whole idea of what's happening in the forward pass of diffusion model. The interesting part is that, as I said, our final goal is not to make images noisy. Our final goal is to get a model which is able to start with a complete random noise and generate some plausible images, as I said, in a backward process, basically. The forward process, as I described it, is very analytical. It's just a mathematical formula. You just start with image and gradually add noise to it, like Gaussian noise to it. And there's nothing to learn. The problem is that it's not clear how to do the backward process of it. We will get in a second how we do this. But the idea is that if we are able to do this, if we are able to learn this backward process, we pretty much can just sample random noise, get it through the model, iteratively denoise it, and get some plausible image. And as I said, that's something we need to learn. So I'm not sure how important it is in terms of like high-level understanding of what's happening in diffusion models. But if we give the model enough steps, right? If this t value here is large enough, let's say 50, 100, some people use like 1,000 steps, we can assume that getting from step xt to xt-1 is like a Gaussian distribution. So in order to implement it, we also say that the only thing our network has to learn is the mean of the denoised version of an image, let's say. So if we would parameterize it, once again, I'm not sure if you really need to understand this formula. I added a slide which is more visual. I think it's simpler to understand. When you have nth step of diffusion, so you have this noisy image on the right. For example, the first step or the last step, let's say, would be complete noise, and you want to make this one step to denoise it. You assume it's normal distribution, and the only thing you want to learn in this normal distribution actually is mean of this distribution. You assume that variance or covariance matrix of it is just identical, let's say. So once again, our model in general, like the neural network that we have, it takes the noisy version of the image and try to make it less noisy, right? When we train our model, we have pretty much two steps. As you can see, at first we start with just sampling a random image from the data set we have, which is just a clear version of this image. We add some noise to it. That's going to be our first step of training. The second step, we take this noisy version of this image, we add a bit more noise to it, right? As you can see in this plot below. And we also, so we have two versions of noisy images, but we also remember the noise we've added. So the model that we have, the diffusion model, is in general, people use simple UNets. Do we know what is UNet? Okay, so it's just basically a model that takes pretty much an image and returns something that has the same spatial size of this image. As I said, we have noisy version of an image. When we pass it through the network, we are trying to get something less noisy. And it's going to be one step of the diffusion, right? So after we get this less noisy version of an image, we can just plug it back to our network and try to denoise it once again, and then take the output and plug it as an input and then denoise it once again. And if you do this like 10 times or T times, you would get these diffusion process. You start with complete noise, then doing it iteratively, you get something denoised. So you end up with a proper image at the end. Yeah, I'm not sure if we really need to discuss the algorithm here. If you want, you can take a look at it after the PDF. I described pretty much the whole training on a high level. I described the training of the diffusion model. And yeah, the sampling also, I think I described it to you. We just sample some random noise, like the random noise which has the size of an image. Then we run our denoising procedure, denoising inference for T times. And at the end, we get the proper image. One thing I wanted to mention is, in general, when you work with diffusion models, as an example, when you work with ChatGPT, you don't really want to generate just random image, which is plausible. You want to generate something that is conditioned. Like when you ask ChatGPT to generate you an image of a cat, right? You expect to get an image of a cat, not just random image. So we have to implement some kind of mechanism of conditioning. As an example, here is a description of some image I want to get. The question is, how do I integrate this information into the inference? Pretty much the simplest way to do this. There are more elaborate ways to do this, but the simplest one is just to add this text, for example, with text transformers, sentence transformers as an input in addition to your image. And so basically at the end, you have three inputs. You have noisy version of an image, the text, like representation of a text, and then the step and ID step, like step number of the diffusion process. And then you just predict the noise you should get, like subtract from your input to get it to make it less noisy, basically. So for this explicit conditioning, as I said in the beginning, when we work just with the diffusion models, you can train a diffusion model just through having a data set of images. You don't really have to have anything. But if you want to add conditioning, like text conditioning, you have to have a data set which consists of both images and some textual descriptions of them. For example, here you have a blue cat. There's a bunch of data sets which are exactly like this. They have both images and corresponding text for them, like a textual description of them. Yes, we actually have, I prepared a couple of notebooks. So let's switch. If you want, you can just scan it. It's just a very short, I don't know, a couple of cells, notebook of like training diffusion model for NIST. I think it takes like less than 3 minutes to run, but yes, I will do this myself too. I'm not entirely sure if you, so when I switch to different windows, can you see it? Okay, let me just change it then.
Excuse me, may I have a question? Like,
Oh, sorry, someone's asking us questions. Sure, yeah.
yeah, like for instance, when we are going backward, we are trying to minimize scale divergence as a loss, as I understood, since
Yes.
we have two distributions. And do we use it as a ground truth, the image, the clear image, or we use, like, for instance, at the time t, we are using the denoised image t minus one
Yes,
as a ground truth?
the second one, yeah.
The second, oh, okay, got it. Thank you.
So yeah, and also I shared the links to those notebooks in the Zoom chat, so you can get it there. So we just start with a data set of images. Probably you know that NIST is like a simple classification task. When we have a set of images, each image corresponds to a digit, like from 0 to 9. We do not really care about classification tasks, so we drop the labels. We just want to learn to generate plausible images of digits, let's say. So yeah, just visualization. What do we have? Those are handwritten images of digits. I think they're like 28 by 28 pixels, so they're rather small. And the first thing we start with the thing I mentioned in the presentation, diffusion, like forward pass. So basically the corruption of an image, right? We have original image of a digit, and then we add some noise to it. We have a function for it called corrupt. Amount is basically the timestamp t which you use for this particular inference, right? So you can see that on different steps, we gradually add more and more noise to the original input data. The model which we would use also is very simple. It's just like a UNAT with some convolutions, which takes an image. Here you have an example, so let's run it too. So if you would just create this model and run through it here it's random, but you can plug images like NIST images. You pretty much, after you run the inference, you get the output of the same size, which is expected in terms of diffusion, because as I said, we kind of denoise the image, right? So we have noisy version of it and then less noisy version of it, so they have to have the same size. Yeah, here is the training loop of this whole procedure. I'm not sure if we should. Oh, sorry, I started the notebook without CUDA. Let me just rerun it. Oh, sorry, I ran out of limit, GPU limit. Okay, let's try to do this with just CPU. Yeah, I mean, it's probably already kind of ran it at the beginning. Okay, so I'm not sure if it's necessary. I mean, I already kind of run it before the presentation. So, but let's just take a look at what's happening here. We have some number of epochs. We iterate through the data we have. And what we do, we just start with generating random noise and corrupt, like noise amount is basically the timestamp, like how much noise do we want to add to the image. We corrupt our initial clear images. And then for each of them, we try to do this denoising process, right? We want to get rid of the noise. And then we just compare the denoised version, which we predict, and actual denoised version, which is like our ground truth. Actually, the question was asked on Zoom was exactly about this. We just compare the denoised version, which we predict, with actual denoised version, which we pre-generated. And yeah, that's pretty much the whole training loop. Yeah, if I would have CUDA, you would see the loss plot, how it drops throughout iterations. But at the end, you have, yeah, after the model is trained, here we have denoising step description. So what do we pretty much have here? We plug, here we have input data, which were like original clear images. Then we add some noise to them and plug to the network to get denoised version. So yeah, the middle one is corrupted data, and the last one is network predictions. So you can see that our model tries to produce less noisy version of inputs, basically. And here, yeah, here's just an example of the whole inference. As you can see, the final results are not like super great. You would get better results if you would play with the network architecture or if you would just try to train it for a longer time. But on top left, it's pretty much initial inputs, as I said, complete random noise. Then we try to denoise them to get the predictions on the right. Then we plug them back to as inputs, adding some noise. I missed this part that we actually add some noise to the inputs when we run generation, but I'm not entirely sure that it's like crucial detail to mention. But once again, so we generated something less noisy, added a bit noise to it once again, plugged into the network, denoised it once again, then iteratively repeated, right? And at the end, the write down images, like right bottom, let's say images here are our final results. But as I said, if you would train it for a longer time and if you would play with the architecture, you would get better results than this. Okay. Yeah, hopefully you got some high-level understanding of what's diffusion. Yeah. Let's then switch to the next part, which is visual perception. Once again, here I just wanted to give you a very high-level understanding of what's happening, because in general, when people kind of talk about machine learning, let's say on a high level, we just cover very simple tasks as image classification or something like this, which are not the kind of I don't know, the most complicated tasks we're trying to solve with neural networks. But let's just gradually start like one by one with how the whole field was developing. So as I already mentioned, we already saw this example of MNIST. I think that was one of the early, it was like a breakthrough in the domain when people learned how to classify images with like simple MLPs. Which was pretty much like image classification task. Then throughout the years, we were able to scale it up to solve tasks which are not like classifying image digits, but classifying like, I don't know, solving the classification tasks with thousands of classes as ImageNet. ImageNet was one of the also like the biggest things in early 2010s, maybe even earlier a bit. So yeah, just like I don't know, some history information, right? In 2012, we had this ImageNet large scale visual recognition challenge. And I think so a couple of years after this, models like neural networks were able to surpass the quality of classification quality, classification accuracy of human performance. And after this, people started trying to apply neural networks to something more elaborate, let's say. One of the examples is object detection, which is somewhat similar to image classification, but it also has a lot of kind of differences, which are kind of important. For those who don't know what is object detection task, is like when we have an image and we are trying to put a box around the object of interest. For example, here we can, for example, try to detect a dog and a bike and a car in the background. I probably are not gonna go into detail describing what's happening in terms of how the networks is constructed, let's say, how it works, but just wanted to give you an example of a task we were able to solve with neural networks, which gave us like pretty much good performance in terms of detection. One of the famous models, I just mentioned it here, it's YOLO family of models for detection, which is used basically everywhere. I wouldn't be surprised even if one of those is running on your iPhone. Even in the background when you're not using your image app, your iPhone is running some detection models on it. Another example of the task which we were able to solve with neural networks is depth estimation, which is an example of a task which is used in such domains as robotics. Let's say we can use depth estimation for localization. Surprisingly, for example, when you have your Roomba running around your house, it's very probable it has something deployed on it because your Roomba has to understand the geometry and the room it's located in to be able to kind of, like cover the largest portion of the surface to clean, and et cetera, et cetera. Just one, I wanted to mention it very shortly. I'm not going to describe it in too much details. But let's try it once again. Raise your hand who know what is visual transformers. Okay, some people know. Since you already you covered transformers in these lectures, we'll shortly describe what's going on there. As you probably remember, transformer models, they work with the so-called tokens or queries or whatever you would call it. So you have some number of inputs you plug into transformer, and with the tension layers, you are trying to produce activations for each of those tokens. When we work with text, it's rather simple to understand what is token, right? We, for example, in context of text, we can just break it down to words or letters or some pairs of letters. In terms of visual transformers, the idea was just to kind of break it down to patches, right? You have an image and you just kind of extract some patches which have some size like 3x3 or 5x5. It depends on your task. And you treat each of those patches as a token, which you pretty much plug into your transformer model after. I think nowadays, so for example, here I added the segmenter model. It doesn't really matter the name. There's a bunch of different transformer-based architectures that try to solve the segmentation task. I think in early 2020 or maybe 2019, people kind of figured out how to apply transformers to the object detection task, which I mentioned a couple of slides before. Very similar idea. We just have some tokens, which we process with transformer model. In decoder part, each of these tokens would correspond to one detection, basically one bounding box. Yeah, and so since then, people were trying to apply transformers to whatever task you have, because I think nowadays it's kind of industry standard that people use transformer models because they just bring you the best quality, the best performance. Maybe the major drawback of transformers is that either you have to pre-train them, right? So you have to have significant amount of data for them to work well. But in general, yeah, I think it's like an industry standard. Whatever task you're trying to solve, it's probably being solved with transformer architectures. Here's an example of rather elaborate task, which I was personally working on. It's called 3D object detection. It's heavily used in context of self-driving cars. When you have a car and you collect information about your surroundings, like a 3D scene, through, for example, LiDAR. LiDAR is like a device, let's say, that use some laser technology, let's say, and collects the point clouds, basically the 3D points of the scene around you. As you can, I'm not sure if you can see it. Each of those green things there is just like a point in 3D space, which is being described by three numbers like X, Y, Z. And the task of 3D object detection is to put a bounding box around objects, right? So we want to detect other cars, like you want to detect pedestrians, I don't know, bikes, doesn't really matter. Like any number of classes which you're working with, you want to detect them and use it further, for example, in task of planning, etc. And as I said, even here we use transformer models because they just bring us the best performance. I'm not going to describe this plot here. It's just like an architecture of one of the kind of state-of-the-art models for 3D object detection task. I just wanted to point it out that we start with some point cloud, and probably the most important block of this whole thing is transformer block, which also processes some tokens. In order to get to this third part I wanted to discuss today, I want to give like a practical 3D object detection example, and I want you to answer a couple of questions. So let's assume that we have the following scenario. So we are like a self-driving company. We want to train a model which would allow us to have a self-driving car. We collected n thousand scenes. By scene, I mean this thing I just described, like some road scenario in Paris, because I assume that's Paris here in this picture. I'm not entirely sure, but we can guess that it is. And we have a couple of we know something about the data we collected. For example, the first thing is that all of the images we collected were collected during like sunny weather between 1 and 2 p.m., right? So we do not have any other kind of data. And we split this collected data into train and test. We train on the train set and observed very good performance on test set. So all of the cars we wanted to detect in the image in the 3D scene, we were able to detect it, which is good, right? We think like, okay, that's great. Let's deploy to our car and try to drive through Paris. And then, not Paris, but maybe just deploy it on car. Let's assume that we face this following scenario, right? We will try to produce prediction for this image here. What do you think we should expect as a performance here, and why? Do you have any thoughts? What would we get if we would, as I described, we have three things. We trained on Paris during particular time in sunny weather, and then we try to make prediction for this image here. What do you think we would get? What would be performance? Would it be like good, bad, the same?
I think the performance would be worse because the scene parameters are very different from the ones of the samples that were used to train the model.
Sure, yeah.
I wouldn't expect the model to generalize so much as it would get similar performance.
Sure, just to repeat it for Zoom, the idea is that since we have significantly different, let's say, scene situation, right? We have snow and whatever, we probably should expect significantly worse performance, at least not the same that we had for like normal images, which we use for training. Okay, I guess here I don't really have to ask you the same question. If we have like night scenario and we train only on scenes which we collected during the day, we would get exactly the same problem, right? I'm not sure how to describe you how bad the predictions would be. They would be just nonsensical. It's just not going to work at all. It would just, the output you would get from the model is going to be absolutely of zero use, especially in this scenario, because the farther you go from the training distribution in terms of similarity, the worse performance you would get, right? And the same scenario is actually when you, for example, collect data in Paris and then you try to deploy it on the car which you use in US. For some people, surprisingly for me, I guess, because I worked with this a lot, people expect models to generalize, and that's not happening like at all. If you would collect data in some country which has very specific architecture, which has very specific weather, and et cetera, if you deploy it in a different scenario, it's the quality of performance, the performance is going to be significantly worse. Yes, and that's pretty much what we observe. The table, you don't really have to think about this too much. The idea of this table is that people try to do the following. They try to train this 3D object detectors on so like on data collected, for example, in Germany, and then apply to data collected in US, and then observe what's the performance drop. And as you can see, the diagonal, it's like when you train on this and test on the same data set, and everything like beyond the diagonal line is when you like train it on some data and then apply it to another one. You can see that it's almost always worse than if you would just apply it in the same kind of scenario. It's a rather common phenomenon. This kind of data, which is significantly different from something we train the model on, it's called auto-training distribution data. And it's very common phenomenon observing that we get significantly worse performance on this kind of data. I had like a bonus question for you, I guess. When you work with ChatGPT models, or I don't know, any other LLM-based model, you seemingly can ask it whatever question, like you can ask it whatever, and pretty much always you would get some kind of meaningful answer, right? In early versions of ChatGPT, I'm not sure if you ever kind of observed it or you heard about it, people were asking some weird questions like print me a million of hash banks symbols, right? And ChatGPT model were starting to do this, just printing you an enormous amount of these symbols. And at some point, something were happening, and the model would start printing actual text of this, like some textual description, which is absolutely out of context of the chat you would have. Which is kind of the behavior I'm trying to explain you here. So if you would provide model with something which is very different from what it have seen in the training, you would get gibberish as an output. But yeah, still the question. Nowadays, we don't really have this problem. I tried it yesterday. I really tried to input something to ChatGPT in order to get some gibberish as an output, and I failed. Why do you think it's the case? Any ideas? Yeah.
Because so many people around the world ChatGPT a lot and then so that it will just incorporate a lot of scenarios into its model, so that if we ask some question, it's already been trained.
Yeah.
Answered at some point.
Yeah, I think it's the right answer. So I think there's two aspects of it. First of all, they just collected so much data and kind of fine-tuned their models. So pretty much none of the input which you provide to the model would be kind of auto-distribution. Sometimes when I'm working with, if you work with ChatGPT trying to do some code completions or trying to generate some, I don't know, scripts, even in Python, sometimes it can actually, I don't know, provide you with some code samples describing like, okay, you have to do this, you need to install this library, and like providing you with the whole kind of setup of things you need to do. And then when you try to, for example, search for this Python library provided by the ChatGPT, it just does not exist, right? I mean, it just provided you with some random made up stuff, which is kind of can be considered as out of distribution, because the behavior which you would expect is just, okay, I don't know what to do, right? I don't have information. I don't know how to do to do this task you ask me. So even now you can reach to this point. You can find a way to get the out of distribution inputs, but in general, yes, because they collected so much data, it's very hard. And another aspect of it, they also implement some safeguard procedures. Like nowadays, you cannot really ask to GPT whatever you want and get an answer. For example, I don't think you can. If you ask some questions about like I don't know, broad activity, you probably wouldn't get any answer, or you would get an answer like, okay, I cannot do anything with it. I cannot answer your question, because yeah, those companies, they actually also implement the safeguards procedures. So this actually brings us to the topic of generalization. I just wanted to describe it in more formal terms, what's happening, but we already kind of covered it on a high level. So when we talk about machine learning models, one of the assumptions that we have is that the trainings data set, the data which we use for training and data we use for testing are the same, right? As I described, like if we train model in Paris, we expect the model being deployed to the scenes, like on the car driving in Paris. It's kind of reasonable assumption, but it's not the most interesting one. In general, we want to go beyond. So when we talk about real world scenarios, as I said, in theory, those distributions are the same, but in real world, they are not. I just added this comment about Bayesian optimization and active learning. For those who know what is this, I guess you would get this comment, but if you do not know, there are applications where we are specifically search for kind of difficult or unknown inputs for our model in order to improve it further. But yeah, the major point is that test and training distribution in general are not the same. As an example, right, on the left, you can see clear image and some perturbed image with some motion blur. And if you would just train a model on clean images and then apply it to an image that have some amount of motion blur, the performance of it would be significantly decreased, right? When you have a detection model, object detection model applied to it, counting people in the image. And then COVID happened and everyone wears masks and you never train your model on people wearing masks. The performance also is going to be very bad. So these distribution shifts are everywhere. And nowadays, I think people think about this problem more and more, but we still do not really kind of care about it too much, I guess. There are several methods and major directions, let's say, how people try to solve this problem or at least like alleviate it. One of those approaches, like branches of methods trying to solve it, is domain adaptation. Those methods assume that in addition to your training data, and your training data is what is like inputs and outputs, like images and classes, images and object detections, images and segmentation masks, whatever. So you have X's and Y's. So, and you try to predict Y's from X's. When you think about test distribution, in general, people assume that you have only X's. So you do not have Y's. You want to predict them for testing test distribution, but at least we can assume that you have inputs, right? You have images, for example. And domain adaptation methods, we're not going to describe what they are doing exactly, but they assume that you have this testing data, which is very bold assumption. In general, you do not. Imagine that you train your self-driving, your object detection model for self-driving, and then you assume that at least you know all of the potential 3D scenes which your model or your car would encounter. It's just not feasible. There's another branch which is called domain generalization. On a high level, it just tries to make some assumptions about the task distribution you would have, but in fact, it does not really solve the problem. You still have the problem of choice of these priors which you make about the task distribution you would potentially encounter. And the last one, I'm not sure if you heard about this, is also like rather popular domain nowadays. It's called adversarial robustness. It's when you have some data, right, the training distribution, you force your model to work well on the edge cases, let's say, in order to not completely break on potentially difficult samples which you can encounter in test data. So you kind of hope that, okay, whenever I will in real world scenario, whenever I would encounter it, at least my model would not break down. But this type of methods, they also have the same problem. They assume that your test data would be significantly similar to your training data, which is not the case, which is not really a real world scenario. In general, you cannot make any assumptions about the data you can encounter. So I just wanted to give you, I tried to describe the problem, right? So this generalization problem, when you want to go to beyond the training distribution to provide basically plausible outputs and predictions for complicated or significantly different test samples. But also I wanted to give you a practical example of it. There is a, let's say, an approach which is called test time training. It is just one of potential like existing possible ways to solve it. Yeah, I will just describe it to you, and actually we have a notebook about it later. The idea is that imagine that you already trained your model, right? You have this training loops, you design some architecture, collected some data, you optimize the loss function. So now you have trained weights for your model. If you plug some good inputs to it, it provides good predictions. And now you want to deploy it and get also like plausible or at least meaningful predictions for something more complicated than your training data. There's a trick. I think it's not super obvious that people would try to do this, but as you remember, when we train a model, we run this thing called gradient descent or whatever optimizer you would use. We run some optimization procedure, basically trying to find ways which minimize our loss function. The idea is that you can pretty much do the same during inference, right? So when you have a new image coming in general, when we run the training loop, we have x's and y's. And in order to compute loss function, you compare the predicted output and the actual target with each other. And if they are significantly different, you want to minimize this difference. The thing is that during inference, you don't really have targets. You do not have, like, I don't know, image class labels. You don't have object detections. You don't have segmentation. So you cannot really compute the loss using targets, right? But what do you have is this inputs. Here you have this X test. So if you would design some loss function which can compute the loss value based only on the input, you can also run the optimization during inference given this particular input. So the procedure is pretty much the same. The only difference is the loss function does not use targets. You just use probably your predictions and your inputs, but you do not really use targets to compute the loss. So the idea of this test time training approach is that during inference, when you have some new inputs coming in, you just run the gradient descent or whatever optimization you have to adapt your model to this new inputs. Though conceptually, this test time training idea is kind of, I would say, intuitive in a way. It's not super complicated to understand. There's basically no formulas, but it can lead to significant performance improvements on corrupted or out of distribution data, which we can encounter. On the right, you can see an example of different kinds of perturbations or noises which we can apply to an image, like Gaussian noise, whatever, motion blur, zoom blur, different kinds of blurs. And if you would just train your model on clean images and then apply it to this perturbed or corrupted versions of images, the performance drop would be significant. Like if you have ImageNet model, which has accuracy of, I don't know, 90-something% accuracy, when you would apply it to this, actually you have this plot here. The original score, the original accuracy is around, let's say, 90%. And each bar here corresponds to different types of corruptions, right? For example, we can see that when you apply Gaussian noise on the left, the original like blue object, just simple object recognition model, the quality, the accuracy of predictions would be near zero, right? Your predictions are useless, absolutely. But if you would do some, for example, this TTT thing, especially there's TTT online version, but it doesn't really matter what it is, you can get significant improvements in terms of your let's call it generalization. Let's call it improvements of performance applied to corrupted or out of distribution data. So at the end of this part, we also have a notebook with one of those test time training methods. I just want to describe it very shortly. It's one of the original ways to do this test time training thing. Imagine that you work within the context of images, right? You take this image of a bird, natural thing you can do with the image, you can just rotate it. It's one of the what would we call it, like augmentations we can use to train our model. You can rotate it like rotate it 90 degrees, 180 degrees, 270 degrees, and like 360 degrees, and get like different versions of an image. Then you train a model which pretty much tries to predict the rotation angle which was applied to the image, right? For the top image, you want to predict 0. For the next image, you want to predict 90, and etc., etc. And since for these tasks, you rotated the image yourself, you know the target, right? You don't really have to have any classification labels. You don't have to put like, okay, it's a bird there, it's a class of bird. You just know that, okay, this image is rotated by 0, 90, or whatever amount of degrees. So you produce those 4 predictions. Since you know the targets for those, you can optimize your model to basically predict the angle, rotation angle. And after training, you kind of split your model into parts. The first part is like features extractor, let's say, and the second part is the actual head that predicts the angle, the rotation angle. And what you do, you just drop the angle prediction head by now, so you do not really discard it completely, but by now you don't really need it, and you keep the feature extractor and retrain, like fine-tune another head which solves the task of classification. So now instead of predicting angles, you actually try to predict class of a bird. So basically you just try to solve the original classification task you were trying to solve before. Or you can try to solve whatever downstream task you have. You can actually also apply it to an object detection task in a very similar manner. So during inference, as I already described it, since you don't really have a class is something you want to predict. You cannot compute the loss for class. You cannot compute entropy, like cross entropy loss. But what you can do, you can once again rotate your images. For each of these rotated images, you have the angle value that was rotated. And you can use the original, this rotation angle prediction head to make predictions and pretty much compute the loss, which I mentioned here, right? So it's going to be our self-supervised loss. Self-supervised because we don't really need to have any class targets here. And so after you just compute this loss, you run the optimization procedure during inference, pretty much the same way as you've done it for during the training time. Yeah.
Just a question. What's the difference between test time training and pre-task regularization?
Sorry.
There's another concept which is like pre-text or pre-task regularization, where you learn the rotation or the flipping of the image, which helps to generate the format later.
Yeah.
I don't see the difference between this test time training and the pre-task regularization.
I wouldn't say it's like pre-task. Okay, if I understood the question correctly, why would we do this instead of just augmenting images during training to get better generalization? Is it the question?
No. I want to know the difference between this method and then what is known as pre-task regularization. I don't know if you're maybe familiar with it.
I'm not sure. What do you mean by this?
Okay, no, we talk about it later.
No. You can finish your. I'm kind of curious. What do you mean by this?
So the idea is very similar to what you described. I mean, maybe they are synonymous. You learn different augmentations of your images. You learn how it's rotated translated or how it's flipped, or if you added some noise to it, for instance.
Mm.
And once you learn the sort of effects you applied on your image, it's going to be easier to sort of normalize the image, and then it's going to perform better in your classification or your generation task later on.
Okay, so you basically try to predict the augmentations applied to your image in order to kind of flip them back and get the non-augmented version of an image, and then you pass it through your network.
Yes.
I think those ideas are they have a lot of similarities. The major difference is that in what you described, you kind of try to normalize the input in order to get better generalization. So you try to get rid of this out of distributionness in the input. In this case, you kind of do not do this. You just want to resolve the generalization problem through this optimization, like test time optimization, basically. Because in what you described, you don't really run any optimization. You just purify the input, basically, right? Yeah. So I think it's a good question. What works better? I wouldn't say that what you just described is it's a bad idea. I think it's okay idea. But the major difference is that this test time training, the core idea of this test time training thing is that you run some optimization during inference. Does it answer your question?
Yeah.
So, right. So we run the optimization. We basically adapt our model to this test data, which can be corrupted or whatever happened with it. One of the important things about this test time training thing is that so here I described it for images, right? For images, it's rather clear how would you perform augmentations, but how would you perform augmentation for text? For text, it's you cannot rotate it, or you cannot, I don't know. There are some ways to, I don't know, corrupt your text, but in general, it's not as obvious what you would do with it. So this test time training idea is very generic. It can be applied to many types of data. For example, I don't know, I worked with graph data, and in the domain of graphs, when you use, I don't know, graph neural networks, which you probably covered actually. Yeah, so like it's super unclear what you would do as augmentation to a graph. I mean, it depends on the context you work with, what kind of graphs you're working with, but it's significantly less obvious to design some augmentation to it. So one of the advantages of this test time training thing is that you don't really have to think about this. Just, I don't know, design some self-supervised loss and you're good to go. Yeah, we have another notebook.
Yeah, just a question. So yeah,
Sure.
There's a lot, you have to kind of like, not a lot, but it becomes very application specific to figure out what type of loss is most appropriate. And then also, since it has to be self-supervised, how you would perturb things to kind of make sure they match.
Yeah.
To get a good or a bad score with that loss.
I think so. Like there's two major problems with this test time training. So what I described is just a regional idea, which was published, I don't know, maybe 5 years ago. Since then, people were trying to solve two major things. Is that people try to make the self-supervised loss as general as possible. For example, this method is also only applied to images, right? But the idea itself can be applied to many other domains, but we just need to come up with some self-supervised loss, which would be like uniform, let's say generic. So people try to resolve it in this way. And another way, you just want to get to design a self-supervised loss, which would bring you the best performance, because not all of the self-supervised losses are meaningful. So, yeah. Did I answer your question? I'm not sure.
Yeah.
So yeah, if you want to scan it, just do it right now. I will also switch to the notebook myself. So you should have opened this test time training for corrupted monist thing. There's like elaborate description. If you would actually open this torch TTT thing, it's our GitHub page. Stars are welcome. We're trying to develop it for people to use.
The library
I mean, it's my idea. I just really like this test time training thing as a tool, let's say. And we started this initiative, let's say, trying to gather existing test time training methods and just kind of wrap them in the way that it would be very easy for people to use. Because in general, when you just read this any test time training paper, it's not super obvious how exactly you would apply it in your
like multiple modalities or just vision?
so like in general it's only me actually. So yes, I'm trying to I try to kind of implement it to I try to implement kind of popular approaches, test and training approaches already existing, but in general I really want to make it like widely applicable, right? Not only images. Actually, I'm not sure if you're interested in audio stuff, I guess. For example, audio, since you probably work with audio as images, right? You already kind of can apply some test and training methods which work with images, but I have never done it. So I cannot tell you how exactly it works. So let me try. Okay, I guess it doesn't really require GPU to run. It's a very simple example. So what we would start with, we have some simple model. We still have the same MNIST data. And yeah, we just train our model on clean images without any augmentations, just their original MNIST data, which the visualization for it, you can see here, just old-fashioned MNIST inputs. Just give me a second to train it. I think it takes like less than a minute to train. Yeah, and after this, we would do the following. As I described, this generalization problem is, we can formalize it as auto-distribution data or like corruption data. I will show you that just applying this Gaussian noise, which we also saw in slides, the performance of your model can significantly decrease. Yeah, just give me a moment to train it. Or maybe actually I don't really even have to rerun it. I already have everything printed. So yeah, as you saw, this is something you use for training. Our model gets, I don't know, 95% accuracy, which is fine for us. Let's say we assume that this quality is okay for us. Yeah, okay, 98%, 97%. But when we apply the Gaussian noise to images, we get something like this as inputs, right? It's even for a person, like for a human, it would be significantly harder to classify them. For example, the third image, I'm not even sure what is it. So we probably should expect some drop in performance, drop in classification. So here, if you would just run this cell here, you would get the accuracy on the corrupted data, right? And so from 98%, we just go below 50%, like 49, which is a significant drop. Yeah, with this, I just wanted to show you that, yes, this corruption or the distribution thing, performance drop is like evident. We have it. Then, yeah, we will install this torch TTT library thing. I tried to make it as modular as possible. I will try to convince that it's very easy to use. We will use this class called TTT engine. The library is designed in a way that these different TTT methods are kind of wrappers over your model, right? So you just, as you can see here, you have your network architecture. You just provide you just initialize TTT engine class with your model and use it in the similar way as before, basically just switching from model train to engine train. And the second change is that when you run inference, instead of getting output, only output is a like single output here, you also get loss TTT, as I mentioned. So all of the test time training methods, they also produce some self-supervised loss, which you use to optimize your model during inference. So here you have this additional loss TTT, which you just add to the final loss here with some weight. So literally minimal changes in terms of training procedure. And let's train it once again. All right, so in terms of changing the training procedure, it's just like a couple of lines. It takes a bit longer to train because you have to do some like additional computations when you train a model. But now what I want to show you is that when we will apply this test time training thing, the performance of our model would significantly improve, right? So it's kind of for free if you just apply this test time training method. So if you do not do this and apply your model on corrupted or out of distribution data, you would get lower performance compared to what you get on the good testing data. But if you would just apply this optimization during inference, you can get significant boost in performance, which is kind of very nice thing to have.
Excuse me, while the model is training, like, what is exactly TTT loss? Is it just the same cross-entropy loss that we are applying for classification?
In this case, in this
Yeah.
in this case, so here we also use the method mentioned in the slides, which is like rotation thing. And rotation task is basically like four class classification, right? It's either 0, 90 degrees, like 180.
Okay.
So in this way is yes, it's going to be just cross entropy loss for a classification task that has like 4 classes.
Okay, got it. Thank you.
Yeah, no problem. Scaled down in terms of what? Can you reformalize your question? I'm not sure if I understand it. Yeah. Yeah.
It's more important that you don't predict current.
So in this code, if we go, yeah, this line here, I mentioned it. So like, since you have this additional loss, I mean, if I understood your question correctly, you have the original loss of the original task and you have this additional part. How do you kind of balance them? Is that the question? So yeah, I mean, you don't really want to turn your model into like a solely angle prediction model. You want to solve a regional task of classification, but you also want to get this second part. You also want to predict the angle. So you kind of have to play around with the weight. Here, there's just a weight coefficient, which we add to the second loss. So we do not really normalize it to get the same scale as the regional classification loss. We just add it on top, right? But yeah, I think it's important a question how to choose how you should balance those two. That's something you just need. It's just like hyperparameter of your model. Does it answer your question? Okay. Yeah. As a concept, yes. So it depends on how do you use, so which kind of input do you have? Do you have like images stacked together as like one big image? Yeah, but what kind of what is the shape of input? Do you just stack all of your how would we call it? So image video is just like a series of images, right? Do you stack them together or how do you process them? What is the architecture you use? I mean, in general, you can figure out how to apply it to videos, I guess. There are no papers specifically targeting video inputs for TTT. So, I mean, if you want to write a paper, you can try it out. But in general, it's possible to adapt it. I'm not entirely sure it would work right away if you would just plug this TTT engine thing from the library to your thing, but I need to check it. I'm not sure, but like 90% sure it would. You can figure out the way how to plug it in, but I would double check to be sure. So, yep, where we are, once again, we generate this TTT task is basically a function which adds noise to your inputs and you try to make prediction for them. But now instead of just running inference with your original model, you try to run this TTT thing. Here, I wanted to show you that. So when you run the optimization, you have the parameter, which is like the number of the optimization steps, right? The number of gradient updates you would make. And I hope it will work. I checked it today's morning, and it was working. But the idea is that the longer you optimize, the better performance you get. But also kind of the trade-off is that the longer inference is, right? So you have to run this gradient updates. And so you can see that the when we run like 0 gradient updates is like, I don't know, twice as faster as when you run several gradient updates. But you already can observe that, okay, when we run 0 updates, so we pretty much do not apply custom training, we have, I don't know, accuracy of 42. When we run only 1 gradient update, we will already get accuracy of 53. 2 gradient updates is 59. I think it should reach something like 65 after 3 updates. Yes, since it's just running, we tried to apply these test time training methods to a bunch of different domains like segmentations, graph, whatever, prediction, and it was working in all of them. So you just can get performance boost almost for free. The only thing you need to figure out is the appropriate self-supervised loss you have for your task. But since you just, as I said, basically for free, you get performance boost out of nowhere. So yeah, the final prediction is, I don't know, 63, 64%. So compared to non-optimized version of the model, it's 20%, which is like a significant performance. I don't really remember what would happen if you would try to run it for longer. I would expect some improvements further, but you can expect that it would saturate, right? It's not going to improve to 100%. Yes, so that was the generalization part. Now getting back to, how much time do we have? Do we still have time? Okay, I can do this very fast. No, that's okay. Just I wanted to give you a very high-level explanation and description of this uncertainty estimation domain, which is pretty much the topic of my PhD. In very broad terms, uncertainty estimation is a very long-standing problem in computer vision and machine learning in general. If you would think about more classical machine learning approaches as like, I don't know, logistic regression or like some tree-based approaches like random forests, which are kind of not super popular nowadays, I guess, but even 5 years ago, they were very trendy. And even now, I'm sure that they are being applied to a number of domains. Like in terms of tabular data, I think tree-based approaches are the best. Pretty much all of them have this functionality of predicting certainty of their predictions. What I mean by this, on the example on the right, you have this red dots is the data used for training. It's like a regression task. So you have theta is your input and the y-axis is something you're trying to predict. So this bold blue line is your prediction, like a mean prediction. The dashed line is actual data. And this 2 sigma credible region is basically the region where you assume your correct answer would be, right? So instead of just producing mean, you also have some variance predicted. You say like, okay, it's not this value, but it's within these bounds. So that's pretty much what uncertainty methods want to do. You want to predict some mean and also certainty, confidence about your prediction. It's a crucial feature and I don't know, functionality for many domains where we rely on our predictions significantly, like healthcare. If you predict you have some model that predicts if the patient has some kind of disease, you don't really want to make an error. You don't really want to say that you don't have, I don't know, cancer, and then the patient has it, right? It's like a horrible mistake, let's say. The same thing in terms of autonomous driving, weather prediction. For example, in terms of autonomous driving, it was maybe in 2000, 2017 when a Tesla car actually hit a person because she was walking not on the zebra, right? But just crossing the road in the wrong place, basically. And Tesla's model, like perception model, was not really aware that people can do this. So for segmentation model deployed on Tesla, having person not on zebra is just not possible. So it was segmented as a part of the road, and the planner of the self-driving like car was not able to, I don't know, to avoid this situation. Weather forecasting is another prediction. Financial forecasting is the same thing. We always want to kind of consider our risks when we work with some parametric models, like forecasting models. Yeah, one point is that in those applications, making the predictions, being aware of confidence of the prediction we made has almost the same level of importance as producing any prediction. Here's just like visualization of what's happening, right? For self-driving example, we have an image. We want to predict some segmentation prediction for it, but also we can produce uncertainty, like in which regions we are the most uncertain. There are several types of uncertainty. I'll try to make it keep it very short. The first type of uncertainty is like aleatoric uncertainty. Imagine that you have data. I actually have an example after it. Imagine you have a data, so for some particular X, which you use as input, in your training data set, you have high variability of potential targets. For example, here, right, you have X equal to 4, and the variance of Y's generated like by data distribution is wide. It's not like the same value. If you would measure some, like, I don't know, temperature, and you would say, okay, I would measure temperature for value 4. I don't know, 4, it's some location, you encode it as a number, and you measure it for this location, and each time you measure it, the variance of your measurement is high, right? So that's the situation we call high aleatoric uncertainty, which is irreducible. We cannot get rid of it. It's just like if you ever studied physics, it's like measurement error. You cannot do anything with it. And the second one is epistemic uncertainty. It's caused mostly by the limited amount of data you have, or this auto-distribution thing. So epistemic uncertainty, you can associate it with this auto-distribution scenario, auto-distribution case, where you pretty much just don't have data there, right? So since we work in this particular scenario, we have data something from 0 to 8, and everything on the left from 0 or on the right from 9 is just absolutely non-central. Like you don't have any data there. And as I said, I do not believe that models, like neural network models, in this scenario can generalize. It's, for me at least, it's counterintuitive. There's no information about what we potentially can have in those regions, but also it can happen within the data region. For example, from this 5 to 7 region, we also do not have any data. That's the reason why we have high uncertainty there, because we just cannot produce robust prediction. We can have good guess, but we should be very unconfident, because I mean, this guess can be just wrong. There is like two types of applications of this uncertainty thing. The one, I would call it like safety robustness related topics. For example, you want to understand when you have auto-distribution sample coming in, you want to make some human verification, as in healthcare, your model predicted something, but you want to flag unconfident predictions to pass them to actual doctor, and etc. Another like big branch, important branch of application is exploration related things, but I'm not sure how familiar you are with those active learning Bayesian optimization, like reinforcement learning exploration. It's basically, you can describe it as some applications where you try to search for the most complicated or unfamiliar samples for your model. So like you want to improve your model through, let's say, collecting something you have not seen before, right? In terms of reinforcement learning agents, it's something when you want to try an action which you haven't tried before, just to see what would happen. Like, what would happen if I would just try this and I would get like higher reward, even though in context of my current policy, it's not the best action to try. So in terms of methods, it's probably going to be the last part. I just wanted to give you the high-level understanding of what are methods used for this uncertainty thing in deep learning. So in classical machine learning, as I already mentioned it, a lot of classical methods, they are like naturally account for the uncertainty. But when we apply the same kind of ideas to deep learning, it's not working. Like if some of you are familiar with the Bayesian inference, when we have like, I don't know, linear logistic regression model, it's very easy to apply Bayesian inference to it because it's small. You have very small number of parameters used for this model. But when you have I don't know, even simplest ResNet, you have millions of parameters, and it's just not feasible to apply those approaches. Therefore, we have to develop something more suitable for deep learning task. One of the modern kind of groups of methods of uncertainty estimation applied to deep learning is ensembling methods. The simplest one and probably the most performant is just ensembling. What does it mean? Imagine that you have your classification task, you have some architecture, you figured out the training loop, you use basically the whole training, and you train your model, right? You have something that is able to predict classes for your images. Then just imagine that you do this 5 times. You generate 5 different models, which pretty much have the same accuracy. The idea is that if you would just average their predictions, you would almost always get better. First of all, you would get better accuracy. Second of all, if you would kind of analyze the variance of predictions made by these 5 models, you can tell whether your model is confident or not. So if they produce the same prediction, it's confident prediction. If it's not, then you can say, okay, I'm not really sure that this prediction is confident. The biggest drawback is that you need to run the inference many times, which is a big problem for I don't know, let's say robotics or self-driving applications, because when you work within this context, you have like an edge case, right? You cannot just deploy another model. You have like one GPU deployed in the car, you cannot actually add more. So for this scenario, it's just not feasible. But the biggest advantage is these approaches, these methods they produce the best quality of uncertainty. Just to give you a taste of what's happening in the domain, it's just not a comprehensive list of papers published on this ensembling-based uncertainty methods. Everyone tries to make them faster, consume less memory, and et cetera, et cetera. But as I said, these ensembling methods are difficult to train, slow, and they are demanding in terms of both memory and computations. So for many domains and applications, they are not feasible, they are not practical. Can we do better? We can. There's like another orthogonal direction, let's say, of development of this modern uncertainty methods for deep learning. They try to work within the context of one model, so we can call it sampling free because they do not use any sampling. The biggest drawback is that in general, nowadays, they do not really produce the same quality of uncertainty as ensembling methods. And very often they are limited to a particular task, for example, the classification task, and they cannot really generalize. They cannot, I don't know, you cannot just take this method and apply it to something exotic like, I don't know, graph regression or whatever. So those two would be the biggest drawbacks. But the biggest advantage is that they are fast to train. They're cheap to train, and they're rather fast in terms of inference. And they're very easy to use. Let's say you just in addition to prediction you were producing before, you also produce some uncertainty value. So you can see this trade-off, right? We have either expensive and good quality and cheap but ineffective, right? We want to have both. Can we do both? And that's precisely the focus of the current state-of-the-art research, let's say, in the domain of uncertainty estimation. Maybe the closing word is this generalization, uncertainty stuff, safety-related questions. They are kind of all connected together. For example, when you talk about generalization and uncertainty, sometimes when you I hope that you got some understanding that generalization is rather complicated. It's not easy task to solve. sometimes it's instead of actually trying to produce good predictions on some unfamiliar test samples, instead of trying to actually make predictions, you can just flag them as uncertain. So if you cannot produce some good prediction, at least say that you cannot produce this prediction, right? Which is exactly one of the tasks uncertainty estimation is trying to do, for example, do this relative distribution detection task. Yes, I think that's everything I had. Thank you for your attention. And if you have any questions, I will be happy to answer them. Yeah, I don't know. If you have questions on Zoom, you can ask them. But if we do not, then thank you for your attention, and we are waiting for pizza, I guess.